So I'm going to call basically all this stuff here, you can call it I0. Okay, so you get I0 times the sine of omega times theta. So that's your current. It's some number times the sine. Some number times the sine. If you were to graph the sine function as a function of time, I, the sine function looks like this, right? That's the sine function. So what's the maximum current? What would be the maximum current based on this one? Yeah, I know. It's when you see the sine is a number between -1 and 1. So only this is the amplitude of the current. So the current, that's I0. Okay. Is that clear? So I naught here will be the 2 amperes. How about this 60 hertz? 60 hertz is called the frequency. The frequency is, which is 1 over the period, and it's equal to 60 hertz. So omega is 2 pi over the period, and that's 2 pi times the frequency. So omega is actually 2 pi times 60. 60 hertz.
120.
Okay. So omega is, that's the relationship between omega and the frequency. 2 pi times the frequency. Okay?
I hear you.
So let's figure out what the right side of Faraday's law. So we're going to use this. We're going to use E dot ds over a closed loop will equal to minus ddt of the integral of V dot dA, right? That's the flux. P dot dA is the flux. Now, in this case, since the magnetic field is uniform, although it's changing, it's still same magnetic field, whether you're at the center or somewhere here. It's still the same magnetic field. So just B dot dA becomes just the magnetic field times the area. So you got minus ddt of the magnetic field times the area. Now choose a loop of radius r. So I'm going to choose a loop because the left side here says B dot ds. ds is a loop, a closed loop. And dA is the area bounded by that loop. So the area will be on the plane of the board, and ds will look like that. I'm going to choose a loop of radius r. So I will get this. I get minus the area of that loop times dBdt. Do we agree with that? The area is fixed, magnetic field is the one changing. Yes?
Why does it have radius r, not the radius of 2 centimeters?
Well, I am free to choose. It says E dot ds, right? So any loop inside here. So I'm choosing an arbitrary loop with radius little r. I can choose with radius equal to the solenoid.
Okay.
So, in fact, at the end, that's what we're going
Oh, okay. So right now you're just giving me variables.
Yeah,
Okay.
in general, yeah. So, minus dBdt. And and also we're searching for magnitudes only. Later we will figure out the direction if we want. So the right side, we dealt with it. And in fact, let's write down here, minus, the area will be pi r squared, right? Of this loop, the flux that's going through. Area is pi r squared. And then dB dt, here's B. When you take the derivative, what do you get? You get mu naught n I0, and then an omega comes out, and then you have cosine of omega t, right? The derivative of sine is cosine. So times mu naught little n times I0 times omega times the cosine of omega times t, right? It's a long expression. So that's the right side of this Faraday's law. This is the right side. How about the left side? Let's deal with the left side. Now, the electric field will either be along the loop, it will circulate, right? Clockwise or counterclockwise, one of them. Either clockwise or counterclockwise. At any rate, it depends, right? Whether the magnetic field is increasing at the moment or decreasing. So it would be clockwise or counterclockwise, one of them. So at any rate, the electric field will be parallel to ds, or maybe anti-parallel, one of them. If I go, let me assume the electric field is just going counterclockwise. So I have E dot ds, E dot ds. If they're parallel, it just becomes E times ds, right? If they're parallel, it becomes E times ds. They're parallel, becomes what? E times what?
Ds.
Yes. So I have the integral of E times ds. On the right side, I have all this stuff. This pi, and r squared, and u naught, little n, I zero, and omega, and the sine of omega times t. Is it? No, cosine, right?
Yeah.
It won't matter, but.
What happened to the negative?
And the negative.
Okay.
Now, as long as you're a distance r away, the magnitude of the electric field doesn't change. Is the electric field at this point larger than the electric field at this point?
No.
No. By symmetry, we say it should be the same. So the electric field comes out of the integral. So we're left with this, E times the integral of ds. But what is the summation of ds? All the little segments along the 2 pi r. That's all the segments along the circumference of the loop will be 2 pi r. So I get E times 2 pi r will equal to this right hand side. Pi r squared u naught little n I zero omega cosine of omega times t. Cancel the pi and the r, the pi and one of these r's. And that will leave you with an electric field, E. Good. E equals to 1/2.
It should be negative 1/2, right?
Oh, yeah, that's minus sign, yes, yeah. And you see I'm ignoring because at the end, they want just the maximum field, yeah. But yes, there is that. So I have here 1/2, and I have the R, I have the mu naught, I have the I, no, I have the N, the little n also. I have the I zero, I have the omega, and I have the cosine of omega times P. Now the question says, what is the maximum electric field? What's the maximum? Maximum electric field. The electric field will be maximum when the cosine is 1 or minus 1, right? That's the maximum. So that's where the minus sign will go away. So it's maximum, I guess, when the cosine is negative 1. Negative 1 times negative 1. So electric field will be maximum when the cosine goes away. And I end up with 1/2. And it's also maximum if the radius is as large as possible. If R is as large as possible. Now, what's the largest radius?
2 centimeters.
It's 2 centimeters, yeah. That's the largest radius I can get away with. Because if R is any bigger, what's the magnetic field outside?
Same thing. Oh, outside, 0, 0.
It's actually 0, yeah. And so, I think the question also says within the solenoid. Within the solenoid, yeah. So, yeah, the largest R is just R of the solenoid, right? So, I would put here R of the solenoid, R solenoid. And then mu naught solenoid, right? SOL means solenoid. And then mu naught little n I zero and then omega. And now we can, yeah.
So do we have to know the length of the solenoid in order to figure out?
It doesn't.
Oh, because little n says 2,000 per
Yeah.
meter.
Yeah, for me.
Okay.
So the length of the solenoid will not matter.
Right. But if you gave it to us as the number of turns of length is then we just solve it.
True. If I said 10,000 turns and it's 4 meters long, so it'd be 10,000 over 4.
Okay.
So now you substitute all the numbers, so you get E maximum will be 1/2. What's the radius of the solenoid? We said 2 centimeters, right? Diameter is 4, so 2 centimeters, so 2 times 10 to the minus 2. Mu naught is 4 pi times 10 to the minus 7. Number of turns was 2,000, right? So 2 times 10 to the 3. The current was 2 amperes, yeah, the maximum current, 2 amperes. And then omega is 60, 2 pi times 60, right? 2 pi times 60. Omega is 2 pi times 60. I said it somewhere, yeah, right here. Well, we have to put all these numbers together. Let's see here. So you got 10 to the 4, 10 to the minus 3, 10 to the minus 5. Something times 10 to the minus 4 minus 5. Probably minus 4. Let's see if what you get matches with what I have. Actually, probably minus 3 because all the pi's then multiply together. You get large numbers.
I'm getting
Okay.
1.89 times 10 to the negative 2.
Okay, so 0.019, right?
Yeah.
Okay. So 0.019 E maximum. All right, so just E maximum. So quick check, what are the units of electric field? Magnetic field would be T, Tesla. Volts per meter, newtons per coulomb, yeah. So volts per meter. Volt. So, I mean, you see, everything's cumulative. Although the test will not refer back directly to chapter, whatever, 20?
30.
Or 20? So it's chapter 30, but still, electric field is electric field, you have to know about it. Okay. The next topic is inductors. We're going to meet another circuit element. We met the battery, right? And we met the resistor. We met the capacitor. And now we're going to meet the inductor. The inductor looks like a solenoid. And it will have the symbol of a solenoid. It doesn't have to be a solenoid. It's a wire that's wrapped, something like this. So, inductors.
Is this the chapter 30?
Yeah. Inductors and inductance. So, in our book, they only talk about self-inductance. Self-inductance. There is also mutual inductance. Earlier, we didn't mention it, but when you have the wire loop inside the solenoid, there is something called mutual inductance. But in this case, we just talk about the inductance by itself. So suppose you have your solenoid, right? And there is a current. This is I, the current loops and then gets out. And if the current is steady, then everything's good. The wire, this is just a conductor, right? A solenoid is made of what? Wire, which is a conductor, so everything's good. It's not a resistor. So current in, current out, and it's steady, everything's happy. Problem is, well, not the problem. When you start increasing or decreasing the current. So as you increase the current, what happens to the magnetic field? Let's say you increase the current. What happens to the magnetic field? It will increase. If the magnetic field increases, then every single loop will experience flux through it that is changing. So there will be a changing flux. And then there will be an induced current that opposes this change. So if it's increasing, it will induce a current, it will try to oppose this current by inducing its own little current that goes this way. And that current will be a function of time, in fact. And we're going to figure it out. So this self-inductance, L, inductance, would be defined as the flux over current. Over current. By flux, I mean magnetic flux, obviously. Okay. Maybe it's not obvious. We're in magnetism, so it's magnetic flux. That's the definition of this inductance. All right? Yeah. Yeah. So with this one? For this one? Yeah. So I said if the current is not changing, so the flux will not be changing, and so there will be no induced current. If the current is changing, the magnetic field in this case will be this way, and it's increasing, right? Let's say the current is increasing. So there will be an induced current in the backwards direction to oppose the change.
Is the induced current going to be formed on that wire? I think on the wire.
Yeah, it will oppose this. It can, if it's as much as this one, then they will completely cancel. You get zero. And in fact, it will be. We'll see when we do RL circuit.
So
yeah.
There will be like two current on that wire.
Well, there's a current on top of a current. So let's say you have an ampere this way, and the induced current is 0.1 amperes. So the total current would be 1.9. Yeah. Yeah. So. Yeah. So let's see. Let's first figure out what the inductance is for a solenoid, just to get a feel of what's going on, and then we will see how we can use this. Okay. So here is for a solenoid, what's the inductance? Well, let's figure out first. Remember, the magnetic field for a solenoid is what? U naught times times N times I. Good. Yeah. And little n is the number of loops per length, right? Number of loops per the length of the solenoid. So let me use that. It will be U naught, number of loops of the solenoid, divided by L times I. Okay? That's the magnetic field inside the solenoid. So what's the total flux in the solenoid? That's the magnetic field times what? Let's say you're a loop within the solenoid. How much flux is through you? The magnetic field times your area, right? Are we clear? Magnetic field times the area of that cross section of the wire. So it's the magnetic field times the area. So it would be times the area. That's for one loop, right? But what if if I want to include every loop? So what's the total flux?
Times the number of loops.
Times the number of loops. Yeah. Bang. Okay. That wasn't planned. So B would be mu naught, capital N, over L, times I. That's the B part, right? The area is the area, and then there is N. N comes from the number of loops. So you got the magnetic flux. Sorry, is my table getting on the way? Probably. Let's do this. So the magnetic flux will be this. Mu naught times N squared, right? N times N is N squared, times the area, times the current, divided by L.
Oh, are we not in A?
I will leave it as A. Yeah. As A for now. Yeah, technically, if the radius is R, it would be pi r squared. Okay. Okay. Therefore, inductance, right? By definition, is what? Magnetic flux over current. So it will be mu naught times N squared times the area divided by the length of the solenoid. That's the self-inductance of this solenoid. U naught n squared A divided by the length.
What's the unit for this?
Yeah, so we get to that. It's called the Henry. The unit for inductance is called the Henry, but we know what it is. It's the magnetic flux, so it's Tesla meters squared, right? Magnetic flux is magnetic field times the area, so Tesla meters squared divided by amperes, right? Which is the current. So, so the units will be 1H but 1H is 1 Tesla times square meter divided by current, right? By amperes. But then an ampere is a coulomb per second, and a Tesla is also a composite unit. And so it's, I think in the worksheet I have this Henry in so many other units, and I say which ones are true, which ones correspond to it. So you got like 5 choices.
Is that gonna be a question on the test?
That's actually I don't know the answer to it
Oh.
because I have not written.
I hope not.
So yeah. So that's those are the units. And so now, what is we know that the potential difference across a capacitor would be Q over C, right?
Mm-hmm.
Remember C is equal to Q over V, so Q over C is V for a capacitor. So let me remind you this one. The potential delta V over a capacitor. So let's say your capacitor is minus and plus, and so delta V, so delta V here. So what's the potential difference between the two ends? So delta V will equal to Q over C, right? And I'm assuming, let's say the current is going this way, so this would be a higher potential than this one. Delta V for a resistor, let's figure it out. So here is, no, let's be precise. This is a capacitor, this is a resistor. And if the current is running this way, so what's the potential difference between this end and this end? Yeah, delta V, yeah, it is IR, but in fact it's negative IR, right? Because this end is at a lower potential than this end, isn't it? The current flows from high to low. Yeah, from circuits. V equal to IR, and it happens to be negative when you go with the current in the direction of the current. Now for an inductor, here's an inductor, how it looks like in a circuit. Let's see what delta V is. In the book, they go over a few things to convince you of this, but I don't want to spend too much time on that. I just want to tell you. Suppose the current is going this way. This is the direction of the current. So what is delta VL? Well, let's go to this one. Let's go back to this, right? Go to the definition of L and see what we get. So multiply both sides by I, so you get the magnetic flux. So let's see what we get. The magnetic flux is equal to L times I, right? L times I, is it? That's the magnetic flux. So far, are you with me?
Yeah.
I just multiply both sides by I to solve for Q. Take the derivative of both sides with respect to time. So that's minus d5 dt. That would be minus L di dt. And what does Faraday's law say about d phi dt? Huh? Yeah.
The integration of D and D.
Yes. Yeah. So let me just put Faraday's law in here. What do you call? Looks like this. E dot ds
Negative L, yeah.
is equal to minus d phi dt, right? And that's the potential difference. The induced EMF.
It was there.
I have it there.
On top,
I actually couldn't find it.
increase, below increase.
Above the
Oh yeah,
example.
over, yeah, okay. Yeah, over there I just had the magnitude, right? So, so the induced EMF will be minus this. And so the potential difference, let's agree with this convention. If you're going along with the current, the potential difference across the inductor from here to here, there will be a potential difference of minus L di dt. And I should have allowed myself a little more space. Minus L di.
And DIDT
Is the rate of change of current, right? So if the current is not changing, what's the potential difference across the conductor, across the inductor?
Zero.
Zero. If di dt is, if current is stable, is not changing, then this is zero, then the inductor is just a wire. A wire. Yeah.
So how would you make the current change in like a circuit unless you have to have.
Well, you can use AC circuit, an AC source of current.
So there would be a magnet in it, in the circuit, in the,
So maybe you're using a generator
yeah,
to generate your current and use that current
okay.
to run this circuit.
Okay.
Yeah, yeah. So here's the deal. Remember we did the following, circuits, right? We had the battery, and we had the resistor, and that was good, right? Then we connected several resistors together, in parallel, in series, and not parallel, in series, and so on. Then we added resistors and capacitors in some combination. And we figured how to charge a capacitor and discharge it, right? We did that. Now, we would have to do the same thing. We would do let's say I have a voltage source, I have a resistor, maybe an inductor. This would be an RL circuit or LR circuit. You can have maybe an inductor and a capacitor, right? You can have a capacitor and an inductor by themselves. You can have an inductor and a resistor by themselves. You can have a resistor, inductor, and capacitor. You can have an AC source with a capacitor, inductor, resistor, and some combination of them, right? You can have all these combinations. I mean, nobody is going to tell you you can't connect it in this way. You could, and the question is, well, what's the current as a function of time? Yeah.
Is it possible to have, since R and C also have parallel and series?
Yeah, you can have it. Yeah.
If that's the case for inductor, if it's in parallel,
Yeah.
is the V going to be the same?
We're a little bit ahead, so yeah, let's get to that a little bit later. Yeah, yeah. So we're going to first try to understand the energy in an inductor. How much energy is stored? Well, how much energy does it take to store in the inductor? Or how much energy is stored in the inductor once you have current in it? And then we will do the circuits. We'll start with the simplest one, which is just an L and a C. A charged capacitor and what happens. And then we will build up to an R and an L. And then, time permitting, we will do some AC and how to solve them. So we will, let's do first things first. We'll do the energy. Can I erase? I think you have of circuits, right, in this class? Not in this class, sorry. There is a course at DVC which is all about circuits, right? Yeah, for electrical engineering. Yeah.
Yeah.
So in that, you will learn some more tricks.
Yeah. I think.
Yeah, so energy. Remember let's say I have a resistor. And there is a current I. So if there is a potential difference, if there is a potential difference across the resistor, then the power delivered in the resistor, right? The power in the resistor will be I times delta V, right? I times delta V. And, so the resistor, your circuit, let's say it's connected to a battery, your battery will be gaining energy or losing energy?
Losing.
Will be losing energy because delta V is negative, right? So the resistor will be delivering energy. And so how about in the inductor? Because let's see here. Let's say I have my current this way. The current will start, let's say, at 0, and then the current grows to some steady current. The current will start at 0, and I want my inductor to get, I want to see, let's say my inductor is connected to a battery and maybe a resistor, like this. The question is how much energy will be stored in this inductor? How much energy? Just like in a capacitor, it was 1/2 CV squared, right? In a capacitor. So the energy, du dt, it's I times delta V on the inductor, right? The current through times the potential difference. Because remember what voltage is. It's joules per coulomb. Joule per what? Per coulomb. And so, meaning it takes a certain amount of joules to transfer a coulomb across this potential difference. Right? One volt means takes 1 joule to transfer 1 coulomb across a potential difference of 1 volt. Okay, so that's the power. So I got I. What's the voltage? What's the potential difference across the inductor?
Negative L di dt.
Yes, L di dt, and you have a minus sign. So what the minus sign means, as the inductor changes, your battery is losing that much energy. It's losing this as the current is increasing. So that's negative, right? So your battery is losing that energy. Where is the energy going? Into the, well, it will be heat here in the resistor, and it will be stored in a magnetic field in the inductor. We'll see in a second. And how much is that energy? Well, it's equal to the positive of this value, right? Your battery is losing this, so your inductor is gaining that, right? Your battery's loss is your capacitor's gain, or inductor's gain. So the energy in the inductor itself, it will just be this number. Or not this number, this expression. So du dt, and we want to figure out the energy itself. So multiply both sides by dt and see what you get. So you get du will be L times I times di, right? I multiply both sides by dt, so that's one divided. So we will integrate. Suppose the initial current was 0, and I'm going to integrate from some initial current to the final current. Put a prime, just to have a different variable. So the energy stored would be U equals to, what's the integral of x dx?
X squared over 2.
X squared over 2. So it'll be 1/2 of L times I squared. That's the energy stored in the inductor. 1/2 Li squared. you get that energy back, we'll see, we'll do a circuit on this one. When you disconnect the battery and connect only the resistor and the inductor, you will start to have an energy back. So that is the energy. Now, let's, is that
Yeah, should we call it delta I?
delta I? Why?
Cause it's the change, cause the, current's increasing or decreasing, right? Cause I know in this case you did from 0 to I.
Oh, yeah, if you started from some current to some,
Right.
yeah.
Okay.
So the reason we do from 0 to I, if you end up at an I, how much do you have compared to when you have no current, right?
Yeah.
So, yeah, so let's see now, the energy per unit of volume, the energy per unit of volume. Let me see for a solenoid what this means. For a solenoid, you will have U is equal to 1/2. What's the inductance of a solenoid? What's L for a solenoid? We have it right here, right?
Phi M
That is
over
it. Mu naught N squared A over L. Good. So it's mu naught N squared A, the area of the solenoid divided by the length of that solenoid, right? I'm going to modify this equation a little bit. So I'm free to multiply and divide by the same number, right? I can multiply by 5 and divide by 5 if I want. So I'm going to do that. What I'm going to do is this. I will have 1/2. Okay, please follow this one. So I have 1/2 of mu naught here. I'll put mu naught squared, but I'll put a mu naught below it. So it stays mu naught, right? You will ask why in a second. I will tell you why in a moment, or you will see why in a second. But this is legal, right? Mu naught squared over mu naught is still mu naught. I didn't change anything. N squared, we're going to leave it alone. Okay, N squared, we're going to leave it alone. And we're going to multiply by an L. So what happens to this L? This becomes L squared, right?
Mhm.
Because L over L squared is still 1 over L. Okay. The area, we're going to leave it alone. And then I have the current squared. The current squared, I'm going to put it here. Okay. Current squared, I'm going to put it there. So here's what I have. U is equal to 1/2, actually 1 over 2 mu naught. Let me put the 1 over 2 mu naught here. And then the area times length, I'm going to put it here. So what would remain here? It would, yeah, good. So it's N squared, I squared over L squared. Or mu naught squared, N squared, I squared over L squared. So it looks like this. It would be mu naught squared, N squared, I squared over L squared, right? And this is 1 over 2 mu naught times mu naught, capital N, times I